Okay, so lecture 24, and now we're going to start doing bivariate distributions where both random variables are continuous random variables. So we're going to sort of replace summation now with integration in a lot of places, and the probability mass function is going to be replaced by the probability density function. So let's say I give you a curve, a surface, that's defined on x and y. So we've got x and y are continuous random variables. They've got a joint probability density function denoted f of x of y. How do I know that this is going to be a valid continuous bivariate probability density function? Well, first of all, we will find that f of x of y will be greater than or equal to 0 for every possible value of x and y between minus infinity and infinity. And if I integrate this curve, so what I'm doing now, remember when we did continuous random variables, we were working out, we got probabilities by the area under the curve. Now we've got two random variables. We will have a surface, and we will be calculating the volume under that surface. And so what we should have is that when we integrate over all possible values, so x goes from minus infinity to infinity, and y goes from minus infinity to infinity, we should get a volume of 1. How do we do the probabilities? Well, now we're just going to integrate under the surface and get the volume. So if I want the probability that x lies between a1 and a2 and y lies between b1 and b2, I'm going to integrate f of xy from b1 to b2 with respect to y, and then a1 to a2 with respect to x. Remember, we could change the order of integration as long as we're careful with those end points. So let's do our first example, example 1. So we've got x and y, and they have a joint probability density function, which is basically 1 for x between 0 and 1, and y between 0 and 1, and 0 otherwise. We need to show that this is a valid PDF, and then we're going to calculate that probability. So the first thing we're going to do is we're going to have a look at this surface. So here is an indication. So you can see we've got x going from 0 to 1, y going from 0 to 1, and this is our surface. It's of height 1 between those, and everywhere else I haven't put it, but it's all just 0. And what do we want to do? Well, first of all, an important thing with all these calculations is what we call the region of integration. It's the illustrated here by the grey box. It's the region in x and y that in this case our curve is non-zero. That's the area we're going to integrate over. And what we're hoping is that when we do that integration, we get our volume under the curve, we get something, in this case a cube, that's volume 1. Now, you can do this by yourself. You know that this distance is 1, this distance is 1, and I've told you the height is 1, so 1 by 1 by 1, we know that volume is 1. So this is a valid probability density function, but let's actually go and do the calculation. So what do we need to do? We are going to integrate our function. We can do dx and dy. So x goes from 0 to 1, and y goes from 0 to 1. And how do we do that? Well, what you do whenever you're doing that is you take the inner integral, and in that case, you're going to integrate that as if it was just a standard univariate integral. So in this case, we're going to do that with respect to x. So we can write the outer bits that we've got are dy, and inside we're going to have x goes from 0 to 1. So that is now 0, y, that's going to be 1 dy. Now this is a standard univariate integral, so that's y, 0 to 1, which equals 1. So by doing the integration, we got exactly what we expected, which was that the volume of that cube was 1. So that seems to be a valid probability density function. Now we're going to have to do this integration. So let's go back to the picture and think about the region of integration. So I've illustrated it here. What we need to integrate now is we need to find the volume over this rectangle that will basically be of height 1. So if we look at it, we want to calculate this volume. This height is 1, and again you could work out this distance times this distance times this height and get the volume. But we're going to do that with integration. So let's go and do that. So this time we've got our integration, we've got our PDF, and we will do it again in the order dx dy, although you could change these. And we know that x goes from 0.1 to 0.3 and y goes from 0 to 0.5. So let's write the outside bit. And the inner one, we've got x goes from 0.1 to 0.3. So that's 0, 0.5, 0.2 dy, which is now 0.2 y, 0 to 0.5, which is 0.15. So that volume is 0.15. Okay, so now we're going to look at example 2. And now we have a dependency. And the key thing to note here is that now we have that y is less than or equal to x. So we need to show that this is a valid PDF, and also we're going to do a probability calculation. So let's go and have a look at our curve. So here's our curve. The only time that it's non-zero is it's for height 2, and it's a height 2 when basically you have that x is between 0 and 1, y is between 0 and 1, but you also have the fact that y must be less than or equal to x. So it's this region here. So if we put in our region of integration, here's our region of integration. So now when we have to integrate, we're going to work out little rectangles that we're going to add. So there's a couple of ways to do that, but what we could do is here is we could take x, and x can go from this boundary, which is y, all the way up to 1. And we're going to end up lots of these little rectangles. In fact, we're adding up, these solids, and when we do that, we should get this region, which hopefully is 1. So let's do that calculation. So we're going to do an integration. We've got our 2, and it's going to be dx dy. And we know that x goes from y to 1, as we saw in the diagram, and y then goes from 0 to 1. So we do the internal one again. So it's going to be 2x from y to 1, which is going to be 0, 1, 2 minus 2y dy, which is now 2y minus y squared, 0, 1, which is 1. So it's valid. Let's go look at the next one. So in the next one, we need x to lie between 0 and 0.5 and y to lie between 0 and 0.25. So let's have a look at our region of integration. Here's our region of integration now. So you've got x going between 0 and 0.5, y goes between 0 and 0.25, but also we've got this extra constraint here that y must be less than or equal to x. So we need to integrate that region, and when we do it, we should get this volume here. Okay, so let's do the calculation. We've got now from 0 to 0.25, x goes from y to 0.5 to dx dy, which is 0, 0.25. We've got 2x, so it goes from y to 0.5 dy, which is 0 to 0.25. We've got 1 minus 2y dy, which equals y minus y squared, 0 to 0.25, which is a quarter, minus a 16th, which is 3/16. All done. Next example. Okay, so we can now calculate probabilities, but sometimes you only care about x or y. So remember Larry the Lego man and doing that idea that you're just going to push all the probability to the x-axis or the y-axis. So we have what we call the marginal probability distribution. So we've got x and y, jointly continuous random variables. We've got a PDF, f of x and y. And if I wanted x or y on their own, then I can just integrate out, which is the equivalent of summation. So if I want just x, I'm going to integrate my function over y. And if I want just y, I will integrate, actually this should be an x. Just integrate out x. So let's do an example. We've now got our curve is 2x, and x lies between 0 and 1, and y lies between 0 and 1. We're going to find the marginal. So before we do that, let's go and have a look at our diagram. So here's our curve now. We go between 0 and 1 and 0 and 1, but now it's basically a plane where this is 2x, and obviously y is just constant. All fine. And obviously our region of integration is this, and the volume under that, if we were interested, would be this volume here. And hopefully that's valid, and it should be 1. You can check that on your own. So let's go and calculate the marginals. So first of all, I want to get the marginal distribution of x. So we'll put a 1, so we know it's the first variable that we're interested in. We're going to take our PDF and we're going to integrate over y to get rid of it. So that's 0, 1. So in this case, we've now got an x, but remember, this is about y. X is just a constant. So this is actually 2xy, 0, 1, which is just going to be, we substitute y equals 1 and y equals 0 and take the difference, and we just get 2x for x between 0 and 1. And you can check that that is a valid probability density function. Now let's get the marginal for the second variable, which is our y. That is going to be from 0, 1 to x dx. So we're integrating out x, which is x squared from 0 to 1, which is 1, for y lies between 0 and 1. Okay, let's go back and look at our picture and see what we've done there. So the first time we took all this probability and we pushed it onto the x-axis. So what we ended up with is this, just the 2x. That's all fine. What about the other one? So in the other one, we took all this probability and we shoved it across to our y, and we just ended up with a uniform. Okay, so that's our introduction to bivariate probability density functions. Next time we're going to look at these marginal distributions and use them to test for independence between x and y. See you next time.